Okay, let's get started here. So today we'll talk briefly about project number 3's grading. We will do some multinomial regression and review for test number 3. So save our stats where we're at. Still, there's time to write a letter to the Board of Regents. Details are available at my various social media sites. Myself and other members of the department are still trying. Aaron Blankenship and I had a meeting with one of the regents yesterday to try to convince him to vote the right way. He said he hadn't made up his mind yet, so I guess that's a good sign. And he seemed interested in what we were talking about. Some events that you could participate in. So the American Association of University Professors are sponsoring a number of different events this week. In particular, on Wednesday, there is going to be a funeral procession that starts at the football stadium. I don't know. I think maybe it's a little bit bad taste to do that, but that will generate some media interest probably and get more of the word out there about what is happening. So on Friday is the Board of Regents meeting. I encourage you to testify if you think that what's happening here is just wrong. There's who you email. While you can actually walk up that day and sign a piece of paper saying you want to testify, get your name in. You can do that as well. So I just emailed this individual this morning, and I am the 33rd person who's talking. So far, there are 4 people from the Department of Statistics who have registered. I anticipate there will be a lot more. So course evaluations. Remember, we have this quiz survey thing for this secondary kind of evaluation that's due on Wednesday. Please do it. Again, it is anonymous, but if you are not comfortable still with contributing or answering some of those questions before the course is actually over, you're welcome just to do the first question that says, I'm not going to answer any more questions, and you'll still get full credit, okay? So you have 2 options of how to get full credit for that. The regular evaluations for the class are due on December 13th. And normally I would say with any kind of course evaluation, these are very important. Well, if I'm not here in the near future, I guess it won't be as important as it normally would be. But I would still appreciate you doing these course evaluations because I want to learn about what I'm doing right and what I could improve upon. So, any questions before we get started here? Yes.
One of the questions asked about how much time we spent watching videos. This kind of a niche question. Do you want us to include the most recent one it was kind of imperative that we watched in that?
Ooh, yeah.
It's kind of different than if we watched it.
Thank you for mentioning that because I put that together before I made the decision exactly how I was going to do the last class. Since we're talking about videos, of course, I wanted to make sure I am actually recording. Yes, I do, because obviously you weren't necessarily required to watch that video, but it was in your best interest to watch it. So yes, please include it. And that kind of... So that information itself is primarily for my own personal use because I want to see how much everything's being recorded. I'm sorry, how much everything's being watched. And I can always subtract 90, or not 90, 70, I think it was, 70 minutes from everyone's total, and I can get a range. So thank you for bringing that up. Any other questions? Okay, so project number 3. Not everyone did it, but for those you did, the average points was 8.5 out of 10. So that, again, just goes to the projects and quizzes part of your grade. It just is added to, I guess, the numerator only. There's nothing added to the denominator. That's why it's extra credit. Now, I have to admit, for 1D, I was disappointed on some of the answers. So 1D, you needed to do a principal component score plot. And, of course, on the test, in previous projects, we talked about how those needed to be square and the same numerical range on the X and Y axes. I did take off points if it wasn't, but obviously I took off only extra credit points, not normal points. So please take note of that. I haven't constructed the final yet, but if I haven't said this already, I like to put questions on the final that were missed during the class. So in fact, right now, I am writing a note to myself. PC score plot, question mark, on final. Okay. I'm not guaranteeing it will be there, but I did make a note of it. Okay, so I couldn't decide if I wanted to do the test number 3 review first or do the multinomial regression continuing the notes first. And so I highlighted that in multinomial regression, so it could be a game time decision. I think I have decided that I want to do the test number 3 review first. And if there's still time after that, then we will continue in the multinomial regression notes. Okay? So, test number 3 is on Thursday. It's over discriminant analysis, nearest neighbor classification, logist regression. Notice no multinomial regression. But it also includes the cluster analysis section. And when I was writing test number 2, when I was writing test number 2, I was having difficulty with figuring out how can I ask a question that it was over material that would have been corresponding to test number 2. Okay. And, the stuff that's from page 1 to 25 is basically the hierarchical clustering stuff. And so one option would be not to have any hierarchical clustering on the tests, but I didn't want to do that option. So I had difficulty then figuring out how could I write a question. And I said, okay, I'm just going to write the tests however I want, and then I'm going to go back and see if there's any problems with the questions that I asked. And there was one question, or let's say one part of a question, where, well, I mean by part, like part A of, let's say, problem number 3. There was one question where I could see that a student might interpret it as, wait, that was the stuff that was test number 2 material. Why are you asking that on test number 3 as well? So, what I decided to do then, okay, here's a compromise. Here's what the question, or here's what the part of the question looks like. Explain how the blank method, it's like we're doing a game show, insert something in the blank. Explain how the blank method determined which clusters to join together when going from 4 to 3 clusters. Make sure to clearly describe how distance is defined for this clustering method in your explanation. There was something a little bit similar to that on test number 2. It's not exactly the same kind of question, but this is the question that's on the exam. So think about, well, there's only, I think, 4 different ways that I could actually put 4 different things I could put in that blank. Make sure you know those 4 different things. and that you could actually answer this kind of a question. While you don't know what 4 to 3 clusters means in the context of what the actual problem looks like, you can imagine, okay, well, I'm doing hierarchical clustering. I'm going from 5, 4, 3, 2 clusters, and so on. Well, how do I get from one set of clusters to the next? How do I measure distance? And that should go a long way then for you to figure out, okay, how do I study for this particular question? Are there any questions about that? Okay, so some of this obviously is the same stuff that I've said before for the previous tests. But let's review. You got the formulas and functions PDF. This is closed book, closed notes, closed video. But what you can do is use all the R programs on my course website, the help that's within R itself, and of course that formulas functions PDF. You'll be using the computers in this classroom to take the tests. I will make the test available on my graded webpage at 12:25. So if you're able to get to class early, you have 5 extra minutes. I don't make the test though 5 extra minutes longer. The test, again, will be in a Word file. There will be some stuff where you would either need to use the equation editor in Word, or instead you can use text-based, let's say, explanations of equations. So, the classic example is, let's say if I need to put a mu hat someplace. Well, I can actually spell out M-U-H-A-T. You have, if you need the extra time, up until 2 o'clock to finish the exam. I posted on Canvas a few days ago where you could turn in the test. Just upload the test and make sure you say submit quiz with that. Same format as previously. Make sure you save a copy of your test as well. This can be done by emailing it to yourself after you have turned it in. And we all know that computer problems can happen, so please bring a laptop just in case. Any questions? Okay. The structure of the tests, remember to show your work. I will take off points, especially since this is test number 3. I will take off points if you don't show me how you got a particular answer. Again, this requirement is to your benefit because if you happen to miss a problem, I can look for ways to give you partial credit if you show your work. Same problem types where you got a data set, you're doing some analysis, maybe some stuff in R and other stuff where you're interpreting. Also, there will be a set of questions at the end that are not interconnected in any way that further assess you. Here's what the actual layout of the test looks like right now. It could change a little bit, but I anticipate it won't change much. Problem number 1 on the test is a discriminant analysis and nearest neighbor classification problem, where I'm going to give you a data set to work with. You're going to need to use R, but there will be one part where you're going to need to do some, let's say, by hand calculations. Maybe set up what the actual equation is to do something, for example, rather than just simply running some R code, so that I can assess whether or not you actually know what's actually being done in R. Then problem number 2 is a logistic regression problem, where the first part is basically, you could say, understanding the model itself. There's actually going to be some math involved. The second part has something to do with an ROC curve. Then the third problem is cluster analysis. You're going to have that question that I have mentioned about 5 minutes ago. And so there's going to also be some hierarchical tree diagram interpretation with this. Think about how is the diagram constructed? How do you make a decision between a certain number of clusters? What do you look for? How do you do the plot in R? And I guess in the process of joining clusters that I have there, that's kind of like the question that I did show you. Then lastly, short answer questions. So the first one deals with kind of an overall view. We've talked about a number of different methods here. And I'm going to ask you basically to, let's say, compare two different methods so that one can understand when would I want to use one of the methods versus the other. There's no computations, but just a general question so that you understand why would I want to use this versus that. And then there's one of these questions, or the second part of the short answer question part, is something dealing with one of the practice problems that you have with the corresponding sections of the course. So it should be somewhat familiar to you, but it's not going to be exactly the same. And overall, there is a question somewhere regarding how is PCA, which is obviously from test number 2, how is PCA helpful to interpret the results for what we're doing now for test number 3? Obviously, we just talked about for project number 3 in a case where PCA was helpful, but we know that there's other places where PCA has been helpful in this test number 3 material. And so this question deals with that. Why would we want to even use PCA with, let's say, logist regression or with discriminant analysis or whatever? So that gives you hopefully some ideas of what to expect for the tests. Any questions about that? Okay. So let's do a review here. So cluster analysis. The goals of this section is basically to determine which observations are similar to one another. And then we can put them into groups, which are not known beforehand. We can put them into groups or clusters so we can get a better idea of data. So how do we determine then that observations are actually close to one another? This is where measures of distance come into play. Of course, we would want to standardize as well. Why would we want to standardize? Maybe that would be a better way for me to help with the review. Why would we want to standardize? With the hierarchical clustering methods, we focus on 4 different ones: nearest neighbor, furthest neighbor, centroid, and average. Understand the process, how to implement them in R, the advantages, disadvantages of each. How do you determine how many clusters? That's where the hierarchical tree diagram comes into play. We talked about things about, well, what's a good cluster, what's a bad cluster? PCA again plays a role. Then we also talked about another popular kind of clustering process called k-means clustering. Make sure you understand the process. Maybe I might ask you to do it essentially by hand without really the help of R. How do you implement an R? How do we determine in this situation how many clusters are needed? With the k-means clustering, we have this thing called the cluster seeds. The reason why they're important is because that's essentially where we start the clustering process. So if I have, instead of k-means clustering, let's say I have 5 means clustering, that means k is equal to 5. That means I start off by choosing 5 observations at random and I grow the clusters from there. The key is at random. So that means if I were to rerun the same code again, I get potentially different results. So that's why we always want to make sure we set a seed and actually rerun the process multiple times. What are some, how about we compare hierarchical to the k-means clustering? What's advantages and disadvantages of them? So then we got into discriminant analysis, basically two different types, linear, quadratic, which corresponds to one of the assumptions, and that is with regard to the covariance matrix. Can we assume the covariance matrix for the different groups, or what we call populations? Can we assume it equal or not equal? We then also talked about 3 different discrimination rules to implement these methods, where the last 2 are the ones that we really focused on. The Mahalanobis distance, the posterior probabilities as well. At least, for LDA, we can calculate these things by hand if we really simplify some of the assumptions that we work with. How do we measure then the accuracy? A question I've given before on a test would be, let's say, to compare or name the 4 different ways to measure accuracy, compare and contrast these ways. Or I might ask a question simply like, why is resubstitution the least desirable of these 4? Okay, it has to do with bias. I also wrote a function to help you out, the summarize.class function that we use for a lot of these sections here, or subsections. And how do we determine which observations are not being classified correctly? Well, you could form like a table. If we only had 2 groups to begin with, it would be a 2x2 table. You could look at the results there. We could also, use PC score plots, parallel coordinates plots, so that we can make a determination of where is this not working well? Where is it working well? Make sure, of course, you need to know how to implement this in R. Then we spent, I think, only 1 day on nearest neighbor classification. Well, compare that to discriminant analysis. What's the big difference? Well, discriminant analysis probably has, let's say, the most possible assumptions out there of all these methods. Normality, covariance matrix equal, unequal, for example, where nearest neighbor classification has the least. That's why we do both. Make sure you understand the process behind it. We took, unfortunately, more time than what we would like to understand, well, what happens, if I have these 4 observations here, they're all kind of, or at least some of them are equal distance to one another. What happens when you're dealing with ties? What happens when you're dealing with other stuff? Make sure you understand that so that you could do it actually by hand. We looked at 2 different functions in R that help us implement this. Now, a big question then is, well, how do we choose K? So K now is the number of nearest neighbors. How do we make that decision? And it all comes down to, okay, let's just try out a bunch of different values of K, see which one performs the best, essentially. We can again go back and look at which observations are being classified correctly and incorrectly by doing PC score plots, parallel coordinates plots. Then we went to logistic regression. Logistic regression has a big place outside of this class for other situations. It's extremely widely used. In fact, probably some of you have actually come across it even before coming into this class. Make sure you can state the model, correctly state the model. You can estimate the model, use the GLM function. How can we estimate pi, which is you could just say informally, the probability of success, or in other words, the probability of being in one particular group. Then we use these pies, or the pie hats, to make a decision about, is a particular observation going to be predicted to be one group or another group? So that's where the concept of cutoff probabilities came about. And while intuitively you would think, oh, you're always going to use 0.5, again, we only have 2 groupings here for logistic regression, you would think that you would always use 0.5, but that's not the case, actually. You could get results that you, let's say, prefer by using a value that's higher or lower for your cutoff probability. And that leads nicely into then why ROC curves are so important. That ROC curve with different possible cutoff probabilities really can help guide you to make a decision about what do you want to use for a particular cutoff probability based upon what the sensitivity is, what 1 minus specificity is. So make sure you can construct one of these plots. Make sure you can interpret one of these plots. Now, one little problem that can happen with logistic regression is you can have something called complete separation. You're not going to be able to get estimates of your betas if this occurs. Make sure you understand what complete separation is, and also why maybe it's not that big of a deal when the whole purpose is actually prediction. Okay, so that's all I had prepared for the review. Do you guys have any questions about the tests, about the topics, or anything? I guess I should have also asked, I mean, I don't think there was any problems, but were there any problems with watching the video for our last class? Okay. So do note that if there's no questions, that means we're going to continue in the notes. Any questions about stuff not related to class? No. Okay, so we have this data set that we're looking at that actually I came across through a consulting problem where it was a grain science researcher, and they wanted to come up with a way to predict group wheat kernels into healthy sprout or scab classes, where these groupings were known beforehand. In fact, I don't know if it was him or a graduate student actually visually would inspect the corresponding wheat kernels and make that judgment. But he wanted to get away from somebody actually looking at it visually, and so he developed a process to do some measurements on these wheat kernels. And based upon these measurements, he was hoping that he could come up with a way that would automatically do the grouping just by that. And so this is what the data looks like. There's the first 3 and last 3 observations. We have 275 observations. We have 2 different, well, the variable is called class. 2 different kinds of, let's say, wheat. Hard red winter wheat, soft red winter wheat. So SRW is soft red winter wheat. HRW is hard red winter wheat. But we also have other measurements like the density of the kernel, the hardness, the size, the weight, and the moisture. The type variable is that corresponding thing that we want to try to predict. Healthy, scab, or sprout. And so in the video, we actually read in the data. Here's a nice parallel coordinates plot to help you see what's going on here. And what we're looking for in a plot like this, if we want to make a judgment of will some kind of method work to try to differentiate between the different types of wheat kernels? What we're looking for here is, are particular types of wheat kernels kind of separated from the other ones? And we do see some separation, but we see a lot of overlap too. In particular here, we can see that the scab looks probably the most different from the other two types of kernels because of what's happening with the density, what's happening with the size, and what's happening with the weight variables. Those green lines are down below. But, perhaps like the density, notice how the black lines, which is healthy, notice how they kind of are like higher than most of the other ones. It's not perfect. But what this is saying here is that, hey, you got a shot here. You should investigate using statistical methods if you could actually predict accuracy these particular wheat kernels. Okay, so then this is where we, at least what I record is where we left off then in the video. And so what we need to do now is a principal component analysis as well. Note that, and we'll come back to this also later, note that I make one little change to the what's called the class variable, which is hard red winter wheat or soft red winter wheat. I need to actually create an indicator variable myself for it because it needs to be numerical. Right now it's just HRW, SRW. So I use the if-else function to help me create this numerical variable. This is, again, an indicator variable. And then I put that variable along with the other variables into printcomp and do a principal component analysis similar to what we've done before. So based upon this, how many principal components do you think we need? Of course, there's probably more than one answer. Yeah, probably 2 or 3. 3 gives us, I think, 80%. Yeah, 80% of the total variation. But we can still look at 2. And while it's not necessarily important for us to do this right here, one could also interpret these principal components. So notice how principal component number 1 is a contrast between the hardness and all the other ones. And so this is what we get. So notice, similar to what we saw with the parallel coordinates plot, I'm looking at the plot on the far left right now, we are having some separation between the greens, which is the scab, and the other types of kernels. Okay, so again, this is giving us some evidence that maybe we might be able to do some good here using a statistical method to distinguish between these methods. I think it's a little bit harder for the reds and the blacks to say that there could be much done to distinguish between those two. We can also take a look at the plot on the right where I do a bubble plot where the bubble size corresponds to PC number 3. It's kind of hard to make a judgment of if that third principal component is really helping to distinguish, at least from this particular plot. Do note probably in the kind of the right side of it, we do tend to have larger circles, meaning larger PC number 3 values. And then we also have some 3D plots here. And here's one that I can actually rotate. Let me make this a little bit bigger. So, again, we can see how the greens kind of distinguish themselves to some respect in comparison to the reds and the blacks. If I come under here, you can notice how some of the reds go down farther than the blacks. So that might be an interesting thing to know. Notice how there seems to be a little bit more blacks up here versus the reds. And that was just, if we look at the PC score plot that was the bubble plot, that was a little bit harder for us to see. Maybe because of all the overlap that we had in that plot too. Okay, so maybe PC number 3 can be a little bit helpful. And so here are my comments. Let me make sure I talked about all those. So I guess the last bullet here is it's doubtful that we'll be able to get 100% accuracy. So coming into this, that's what I would expect. Again, by just looking at the parallel coordinates plots and the PC plots ourselves, that is not a foolproof way to say yes or no. I would be able to get 100% accuracy because it's just hard for just humans to be able to see that indeed there are patterns over these multiple variables and stuff. So what we're going to do then is estimate then the following multinomial regression model. So again, a multinomial regression model is basically the extension of a logis regression model where the number of groupings, categories, or populations that we have for the response variable is 3 or more. You could say 2 or more. Basically, in the multinomial regression model then just simplifies down to a logis regression model. Most people always present them separately, so they don't do just multinomial first and say, oh, look at that special case. People always say logis regression, and then some classes will actually say, okay, well, here's the extension, multinomial. And so this is what our model would look like. On the left side, we're modeling the log of the ratio of 2 probabilities, pi sub j divided by pi sub 1. So that subscript j is either 2 or 3. Remember, we have 3 different types of weak kernels. For now, I will just tell you that j equal 1 will be healthy, j equal 2 scab, j equal 3 sprout. Yeah, okay, I guess I did get to that, yeah. Why is that, though? And this gets to understanding some things about how R does stuff, and it's not necessarily the same for other statistical software packages, so you always have to be careful if you do end up using other ones. The way that R works is that whenever it has to make judgments of this ordering of let's say, values in a categorical variable, it always uses this kind of ordering right here. So it puts all numbers first, then the letters, where the lowercase comes before the uppercase. And so what we see here is that healthy, scab, sprout. Let's put those in alphabetical order. Healthy would come first. So that's why j equal 1 corresponds to healthy for R's way of doing this. Scab, SC, comes before sprout, SP. So that's why it's 2 and 3 for scab and sprout. Now on the right side of the model, then we have the traditional linear combination of the betas with the independent variables or explanatory variables. The key that's different than what probably most of you have seen before in a class is that notice we have a subscript j there. And the reason being is because you can actually rewrite this model like this, where I have log of pi 2 divided by pi 1 is equal to beta 1 0 plus, beta 2 0. Beta 2 0 plus beta 2 1 times the class plus and just so on. And also you could write the model as log of pi 3 divided by pi 1, which is equal to beta 3 0 plus beta 3 1 times the class plus and so on. So that would be one other comparable way to write the model. The way I wrote it here was just a little bit more compact, because then I can just say j equal 2 and 3. Okay, so let's look at how to estimate the model. So there's a function called multinom, which typically is used the most to estimate a multinomial regression model in R. There are other functions out there. The reason why I choose this one is because this one is in the base, or I'm sorry, it's in the default installation of R. Other ones are not. And so my default always, whenever I do teaching, is I always go and use the function that is in the default installation and look to see if there's advantages to using other ones in other packages. There can be some small advantages with respect to this model, but not enough that's worthwhile for us to introduce here. In my Stat 475, 875 class, I will talk about at least one other one. And the package that multinomial exists in is the NNET package, which stands for neural networks. And it just, you might have heard of neural networks before, it just so happens that the person who originally programmed this in drew some connections between these models and neural networks, and so this is why the function exists in that package. This package, again, is in the default installation of R, but you do need to always say first, library NNET. This, getting to R's way the R works, this package is not on the search path for R when you just open up R automatically, or when you first open up R. And so that's why you need to tell R, put this package on the search path. Okay, so I'm going to estimate the model. The way to use this function is pretty standard. I could say I'm going to put the results in an object called mod.fit for model fit. Gets the results from multinomial, where I put for my formula argument what I want R to estimate for the model. So that grouping variable, or what we often think of as a response variable for a regression model, that comes first. That's my type variable, tilde, and then I put all the corresponding independent variables, and then simply I put in my data. We will have some stuff that's printed that talks about the numerical iterative estimation process. How this is done has some similarities to what we did for logistic regression. It's not worth for us to get into those details. But the key thing to look at right here, converged, meaning that this numerical process did get to these beta hats that don't change hardly at all for more iterations. Then we can use the summary generic function to summarize information that's inside of mod.fit. And this is what we get. So we have a table labeled coefficients. And typically in any kind of regression output, you see tables labeled like coefficients, and that's where you would find your beta hats. And indeed, that's what happens here. Now remember how R associates with scab j equal 2, and then with sprout j equal 3. So what that means for us then, corresponding to these columns, this 30.5465 is beta hat to 0. The 19.16 is beta hat 30. And let's just do one more here. This negative 21.59 under density would be beta hat to 2. And then we have another table that's labeled as essentially standard errors. What that means, for example, this 3.11 square root the estimated variance of beta hat to 2. So based upon that table there, what you have learned in other, let's say, regression modeling settings here, is beta to 2 significantly different from 0, do you think? Yes or no? Sure. So based upon what you've learned in other regression settings, maybe this class or other classes, when you see that beta hat, when you see that standard error, do you think that beta to 2 is significantly different from 0? In other words, let's say if I wanted to do a hypothesis test like this. Would I end up concluding reject HO or don't reject HO?
No, reject.
Reject why?
Like saying it's not zero because varying by 3 would take a lot to get to 0 from 21. Right?
Yeah. So find the ratio. So if you've the test statistic that's normally presented is a z, negative 21.597 over 3.11, which we approximately, let's say about 7. Use a standard normal distribution approximation. And that then would be very unusual. And so that's why we would reject. Now, why I asked that question, just to help reinforce stuff that you've done in other courses and to help you understand how you can apply that to a new situation here. You know, the purpose in this particular class is not doing inference with like that, but rather we want to use the model for prediction. But I'm just pointing some stuff out here. So I'm not going to ask you a question to do that on a test. Now, one of the things that you should do whenever you're working with, let's say, an unfamiliar function, you know, after you've fitted the model, well, you probably want to see what's actually stored inside the object that I got back. So we say names mod.fit, and we can see the information that's stored there. One thing that's in particular that's important for us is something called fitted.values. So that typically means predictions or estimates of your response, let's say. And if I look at the first 6 rows of what's actually in there, this is what I get. This is pi hat 1, pi hat 2, pi hat 3. We'll talk about that more, how that estimate comes about later. But again, I want to introduce some intuitiveness here. So the estimated probability of that first kernel being healthy is 0.855 based upon this model fit. So if you look at those 3 probabilities there, this all are probabilities corresponding to these 3 groupings for observation number 1. If you had to guess if it was healthy, scab, or sprout, what would you choose? Healthy, yeah, because it has the highest probability. That's simply how you use this model to do that prediction that we need. That's it. Now, also when you're working with an unfamiliar function, you know, you often want to see, well, what's the class of the object that's returned to us? Here it's actually 2 classes, where the first one is what plays the biggest role here, multinomial. And so if I wanted to see all the corresponding generic functions that are associated with objects of this particular class, I can do methods class equal multinomial, and we can see, for example, there's that summary that we had used. Okay, so let's look at one particular thing here. Remember that the class variable in the data set itself was categorical in nature, had levels of HRW and SRW. And depending upon what your background is before you got into this class, you might be wondering, wait a second, how can this model be estimated if I have this variable that doesn't have numerical values in it? So let's talk about that. Notice what R does in this output that I skipped over. So we have this column, just like with all the other variables, that has my beta hats. It's labeled as class SRW. So what R has done, it has created actually an indicator variable for the class where when you have a level of SRW, that's when this indicator variable is a 1. Otherwise, then for HRW, it's a 0. So the key is that R has created a new variable called class SRW that is a 1 or 0, a 1 for SRW. Now, how would I even know beforehand that that would occur? Well, it kind of corresponds to some stuff that we were talking about. So if I use the function levels in R, levels wheat $class, R will tell me, okay, well, what are the different categorical values? And we see HRW, SRW. Notice what comes first. HRW. The way that R operates then is that is always set to the level of 0. The next level will be 1 for that indicator variable. Notice how, let's compare this to this. So just a few minutes ago, we were talking about, and I skipped over this part right there. You know, the alphabetical ordering of the different types of wheat kernels. R then assigns a level of j equal 1 for that first level. And the reason why that's important is that basically in our model then, this is the base level that we do all our comparisons to. Now, relative to the class variable, this HRW essentially becomes the base level for a particular variable. It is a 0 in this particular case, where, let me actually even go a little bit further, and that will make more sense, that explanation. Suppose instead I had a 4-level qualitative variable that had levels of A, B, C, and D. How would R take that into account? Well, it would create 3 indicator variables as shown in this table, where the second level becomes the first, corresponds to the first indicator variable. So let's say I have an indicator variable called x1. That's going to be a 1 when I have a level of B, 0 otherwise. x2 is going to be a level of 1 when a level of C, 0 otherwise. x3 has a value of 1 for a level of D, 0 otherwise. That first level then becomes what's called the base level. And essentially, you're always making comparisons to that base level. So here's a question for you that hopefully some of you have seen in another class. Why would R make only 3 indicator variables here rather than making 4? Because after all, we have 4 different levels. Why would R do this?
Is it just because it's more simple? There's no reason to have a 4th one, but you can do it with 3.
Why can you do it with 3 though? Why not 2? Why not only 1?
Because you wouldn't be able to differentiate with only 1 or 2.
True. So are you saying with 3, that's the lowest number where you could differentiate between all the levels? I think that's what you wanted to say.
Yeah, but now I'm thinking about it.
Well, I was hoping to guide you there. Yes, that is correct. So think of it this way. Notice how all 4 of these levels have a unique coding corresponding to just having 3 indicator variables. That's why only 3 are needed when you have a 4-level categorical variable. So this kind of a topic, I talk about this in my Step 475, 875 as well. But typically the first time that someone sees something like this is when they really get into more detail regarding regression analysis. But it's used outside of a formal regression model too. Anytime that you have a qualitative variable that has more than 2 levels, you need to know what's going on. You need to know how the software package, there's actually other ways to do this, how the software package is going to create these. And so this is how R would do it. And also, I guess, just to give you a little bit more background, I'm getting a little bit off track in terms of what will be on a test or not. So this next thing I'm going to say is not on a test. Let's say if I did create X4. You would think I'd probably create it like that. And we know from a regular old regression model, you're going to have like an X matrix, X prime X inverse X prime Y. We talked about that at the beginning of the semester. And many of you saw in another class. Suppose these 4 indicator variables are the only components of X, in addition to your beta 0 column. It's all column of all ones. Okay. What will happen? Something bad will happen if you were to use something like this. I would expect that the stat majors in one of the 300 level courses would talk about this. Fortunately, off the top of my head, I cannot remember which one it would be.
Does it have to do with the singularity, not being able to calculate the inverse?
Say that one more time about the inverse.
Does it have to do with the singularity and not being
Yeah.
able to calculate
Yeah.
the inverse?
Thank you. You wouldn't be able to calculate the inverse. So you would have some linear dependent columns of your X matrix in the end. And so that's why you can't do that. And instead, you'd only use 3. So, especially for stat majors, if that's a little foggy or not clear, take some time to review that, because that's a very important thing. This is a common mistake that I will sometimes see non-stat majors make. And let's say if a stat major is maybe doing some consulting with a non-stat major, let's say outside, let's say after you graduate and stuff, you need to know why you could not calculate a beta hat here. You just can't, because the X prime X matrix is going to be singular. Okay, let's get back on track here. I'm sorry. It's good to know, but we do have a narrower purpose here.
Just one. So if this is the case, that R would automatically create an indicator variable in our instance, why you created the since the class was having 2 categories, you created another variable with the if-else function. So if there was no need to do that, if you were directly put in, so R would create an indicator variable for that.
That's a good question. So towards the very beginning of class, I created a variable called class new. The key was print comp will not do that. And that's why I needed it.
But for multinomial logistic, we don't need that specific.
You don't need it. And the key thing is because you're doing 2 different things. One's doing a regression model, and the other one's not. Okay, so let's actually look at how we can actually write the model out. So, of course, I put hats on top of now the estimated quantities. So I have log of pi hat scab. Scab is 2. I mean, I could have put 2 and 1 there. I just try to be more informative. Log of pi hat scab divided by pi hat healthy. And so we can see, let me get my highlighter out. Here's my 30.55. Here's my 30.55. I continue to write this out until I get to, let's say, there's 0.11 for moisture, 0.11 for moisture. Okay. Now for the sprout part, again, sprout would be 3, healthy is 1. Here's the 19.16. Here's the 19.17, I should say. Yeah, just keep on writing the model out. If I ask you to actually write out the estimated model, of course you have to do both parts, because both parts are the estimated model. Now the next part here I have actually highlighted in green. And that is because, remember, we skipped the factor analysis section of the course. The factor analysis section also had me go into some stuff regarding maximum likelihood estimation. And we did do a little bit of it, but we didn't do all of it. And one part was using something called likelihood ratio tests. And when I was preparing for today, I was like, okay, especially given where we are in the semester, is it really important for me to explain the background in terms of what likelihood ratio tests are? I decided it was not. So you're not responsible for this next little part, but I do want to talk about it some. Okay. So, whenever you estimate a regression model or any kind of model, you often want to use that model to make a determination of, is a particular variable important or not? And so the way that we can do that is with a hypothesis test. So previously we looked at this, I kind of on the fly looked at this kind of hypothesis test for the density variable. And we concluded that we would most likely reject. Well, we would reject, I say. The problem with what I did there, though, was that was not for the entire variable. It was just for one particular, let's say, part of the variable. It was for the scab versus sprout. I'm sorry, scab versus healthy part. What will be more appropriate is to do this. Where now we are testing all the betas in the model corresponding to density. Because there will be two. You have the scab versus healthy and the sprout versus healthy. Okay? And so this will be the better hypothesis test to do. That's why in that summary mod.fit output, you didn't actually see the normal table where you would have, let's say, the z values or the t values, and you would have the p values next to it. That's why that wasn't there. And so if I do want to do this kind of a hypothesis test, I need to use a little bit, let's say, more sophisticated way, using what's called a likelihood ratio test. And we have talked about likelihood functions before, and with the name ratio, as you can imagine, it's the ratio of two likelihood functions. The numerator says HO is true. The denominator is calculated as if HA is true. Okay? And using that ratio there, we can make a determination of is there sufficient evidence to indicate evidence against the null hypothesis. And to do this particular test, again, I will not ask you a question about this on a test. We can use a function that's in the package called CAR. CAR is a companion to applied regression. And we can use a function in it that is called ANOVA. This is not actually analysis of variance, though. If you want to know more why it's called that, take my 475, 875 class. But it's called ANOVA because we're kind of doing some similar things to analysis of variance. And if I say ANOVA mod.fit, now I get my tests. And so we can see for the density variable, we had this, what's actually -2 log of the likelihood ratio. There's a little bit of a mathematical transformation there. I get a value of 90.56. And that value itself is not going to be very meaningful to you because you don't necessarily know what to compare it to. Well, in the end, we compare it to a chi-square distribution with 2 degrees of freedom. And if you're familiar with a chi-square 1, which most of you have, well, you should have all seen before, you can imagine that chi-square 2 is not going to be too different, and it's not too different, not just because it has 2 degrees of freedom, but it's not too different. And the main thing that you can get out of it here is that this p-value is extremely small, and so we would reject, which is not surprising given that when we only tested one of the betas, there was strong evidence to reject as well. So what this is saying then is that density is important. Hardness is kind of marginally. There's some evidence, but it's not strong. And then weight is important. Was there a question?
I was going to ask, why do we not need beta 1, 2 in the hypothesis? Would
That would be for the class variable. Oh, I'm sorry. Let let me restate that. We do not have a beta 1, 2 in our model. That's why. The reason being because if I were to write out my model, okay, that's why. Yeah, it's just something that you have to get used to with these kinds of models. That subscript 1 is not going to appear, at least for the first index.
Because the J would start from 2 onwards.
Yeah. Okay. Okay, let's see where we're at here. Hold on. Okay, rather than starting a whole new part of my notes here, why don't we just end it with that? I suppose if you want to, you might have enough time to participate in Tuesday's activities where you can go to the City Campus Union if you speed down there, and create your own sign to protest what is going on here at the university. Okay. So let's take a look at what else we have then going on here. We only have 3 more regular classes left. Today, I'll have my office hours after class. I can only go till 2:20 because guess why? I have more meetings dealing with this budget reduction stuff. Thursday, we'll have class. It will be test number 3. Again, we can start at 12:25. You can go until at least 2. Looking further ahead, the final exam is due Thursday, December 19th. It is Thursday, December 19th at 7:30 a.m.
Friday.
Thank you. And now I'm going to write a note to myself just to verify that, what? I'm going to write a note to myself to verify that I got everything everywhere else written correctly. Also, we have that quiz/survey due tomorrow. Okay, so please get that done. Are there any questions? Okay, that's all then for today.